So I want to start out with this beautiful picture from my childhood. I love the science fiction movies. Here it is, This Island Earth. And I'll leave it to Hollywood to get it just right. 2.5 years in the making. I mean, even the creationists give us 6,000. But Hollywood goes to the chase. And in this movie, we see what we think is out there. Flying saucers and aliens. Every world has an alien, and every alien world has a flying saucer, and they move about with great speed. Aliens. Well, Don Browning, my friend, and I finally got to the point where we got tired of turning on the TV and seeing the spaceships and seeing the aliens every night, and tried to write a counter-argument to it and put out what does it really take for an Earth to be habitable, for a planet to be an Earth, to have a place where you could probably get not just life, but complexity, which requires a huge amount of evolution and therefore a constancy of conditions. So in 2000, we wrote Rare Earth. In 2003, we then asked, let's not think about where Earths are in space, but how long has Earth been Earth? If you go back 2 billion years, you're not on an Earth-like planet anymore. What we call an Earth-like planet is actually a very short interval of time. Well, Rare Earth actually taught me an awful lot about meeting the public right after I got an invitation to go to a science fiction convention. And with all great earnestness, walked in. David Brin was going to debate me on this. And as I walked in, the crowd of 100 started booing lustily. And a girl came up and said, "My dad says you're the devil. You cannot take people's aliens away from them and expect to be anybody's friends." Well, the second part of that, soon after, and I was talking to Paul Allen, and I saw him in the audience, and I handed him a copy of Rare Earth, and Jill Tarter was there, and she turned to me, and she looked to me just like that girl in The Exorcist. It was, it burns, because SETI doesn't want to hear this. SETI wants there to be stuff out there. I really applaud the SETI efforts, but we have not heard anything yet, and I really do think we have to start thinking about what's a good planet and what isn't. Now, I throw this slide up because it indicates to me that even if SETI does hear something, can we figure out what they said? Because this is a slide that was passed between the two major intelligences on Earth, a Mac to a PC. And it can't even get the letters right. So how are we going to talk to the aliens? And if they're 50 light years away, and we call them up, and you blah, 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 and then 50 years later it comes back, and they say, "Please repeat?" I mean, there we are. Our planet is a good planet because it can keep water. Mars is a bad planet, but it's still good enough for us to go there and to live on its surface if we're protected. But Venus is a very bad, the worst planet. Even though it's Earth-like, and even though early in its history it may very well have harbored Earth-like life, it's soon succumbed to runaway greenhouse. That's an 800 degrees centigrade surface because of rampant carbon dioxide. Well, we know from astrobiology that we can really now predict what's going to happen to our particular planet. We are right now in the beautiful Oreo of existence, of at least life on planet Earth, following the first horrible microbial age. In the Cambrian explosion, life emerged from the swamps, complexity arose, and from what we can tell, we're halfway through. We have as much time for animals to exist on this planet as they have been here now till we hit the second microbial age, and that will happen paradoxically, everything you hear about global warming. When we hit CO2 down to 10 parts per million, we are no longer going to have plants or allowed to have any photosynthesis, and there go animals. So after that, we probably have 7 billion years. The sun increases in its intensity and its brightness, and finally, at about 12 billion years after it first started, the Earth is consumed by a large sun, and this is what's left. So our planet, like us, is going to have an age and an old age, and we are in its golden summer age right now. But there's two fates to everything, isn't there? Now, a lot of you are going to die of old age, but some of you, horribly enough, are going to die in an accident, and that's the fate of a planet too. Earth, if we're lucky enough, if it doesn't get hit by a hail bomb or gets blasted by some supernova nearby in the next 7 billion years, will finally be your fate. But what about accidental death? Well, paleontologists for the last 200 years have been charting death. Strange extinction as a concept wasn't even thought about until Baron Cuvier in France found this first mastodon. He couldn't match it up to any bones on the planet, and he said, aha, it's extinct. And very soon after, the fossil record started yielding a very good idea of how many plants and animals there have been since complex life really began to leave a very interesting fossil record. In that complex record of fossils, there were times when lots of stuff seemed to be dying out very quickly, and the father-mother geologists called these mass extinctions. All along, it was thought to be either an act of God or perhaps long, slow climate change, and that really changed in 1980 in this rocky outcrop near Gubbio, where Walter Alvarez, trying to figure out what was the time difference between these white rocks, which held creatures of the Cretaceous period, and the pink rocks above, which held tertiary fossils. How long did it take to go from one system to the next? And what they found was something unexpected. They found in this gap in between a very thin clay layer, and that clay layer, this very thin red layer here, is filled with iridium. And not just iridium, it's filled with glassy spherules, and it's filled with quartz grains that have been subjected to enormous pressure, shock quartz. Now, in this slide, the white is chalk, and this chalk was deposited in a warm ocean. The chalk itself is composed by plankton, which has fallen down from the sea surface onto the sea floor. So that 90% of the sediment here is skeleton of living stuff, and then you have that millimeter-thick red layer, and then you have black rock. And the black rock is the sediment on that sea bottom in the absence of plankton. And that's what happens in an asteroid catastrophe, because that's what this was, of course. This is the famous KT. A 10-kilometer body hit the planet. The effects of it spread this very thin impact layer all over the planet, and we had very quickly the death of the dinosaurs, the death of these beautiful ammonites, Lascentisrus here, Enceloceros over here, and so much else. I mean, it must be true because we've had 2 Hollywood blockbusters since that time, and this paradigm from 1980 to about 2000 totally changed how we geologists thought about catastrophes. Prior to that, uniformitarianism was the dominant paradigm. The fact that if anything happens on the planet in the past, there are present-day processes that will explain it. But we haven't witnessed a big asteroid impact. So this is a type of neo-catastrophism, and it took about 20 years for the scientific establishment to finally come to grips that yes, we were hit, and yes, the effects of that hit caused a major mass extinction. Well, there are 5 major mass extinctions in the last 500 million years called the Big Five. They range from 450 million years ago to the last, the KT, number 4. But the biggest of all was the P, or the Permian extinction, sometimes called the mother of all mass extinctions. And every one of these has been subsequently blamed on large body impact. But is this true? The most recent, the Permian, was thought to have been impacted because of this beautiful structure on the right. This is a Buckminster fullerene, a carbon-60, because it looks like those terrible geodesic domes of my late beloved 60s. They're called buckyballs. This evidence was used to suggest that at the end of the Permian, 250 million years ago, a comet hit us. And when the comet hits, the pressure produces the buckyballs, and it captures bits of the comet, helium-3, very rare on the surface of the Earth, very common in space. But is this true? In 1990, working on the KT extinction for 10 years, I moved to South Africa to begin work twice a year in the Great Karoo Desert. I was so lucky to watch the change of that South Africa into the new South Africa as I went year by year. And I worked on this permanent extinction, camping by this Boer graveyard for months at a time. And the fossils are extraordinary. You know, gaze ye upon your very distant ancestors. These are mammal-like reptiles. They are culturally invisible. We do not make movies about these. This is a Gorgonopsian or a Gorgian. That's an 18-inch long skull of an animal that was probably 7 or 8 feet, sprawled like a lizard, probably had a head like a lion. This is the top carnivore, the T-Rex of its time. But there's lots of stuff. This is my poor son, Patrick. This is called paleontological child abuse. Hold still, you're the scale. There was big stuff back then. 55 species of mammal-like reptiles. The age of mammals had well and truly started 250 million years ago, and then a catastrophe happened. And what happens next is the age of dinosaurs. It was all a mistake. It should have never happened. But it did. Now, luckily, This Thrinaxodon, the size of a robin egg here, this is a skull I've discovered just before taking this picture. There's a pen for scale. It's really tiny. This is in the lowest Triassic after the mass extinction is finished. You can see the eye socket. You can see the little teeth in the front. If that does not survive, I'm not the thing giving this talk. Something else is, because if that doesn't survive, we are not here. There are no mammals. It's that close. One species ekes through. Well, can we say anything about the pattern of who survives and who doesn't? Here's sort of the end of that 10 years of work, the ranges of stuff. The red line is the mass extinction. But we've got survivors and things that get through, and it turns out the things that get through preferentially are cold bloods. Warm-blooded animals take a huge hit at this time. The survivors that do get through produce this world of crocodile-like creatures. There's no dinosaurs yet. It's just this slow, saurian, scaly, nasty, swampy place with a couple of tiny mammals hiding in the fringes, and there they would hide for 160 million years until liberated by that KT asteroid. So if not impact, what? And the what, I think, is that we returned over and over and over again to the Precambrian world, that first microbial age, and the microbes are still out there. They hate we animals. They really want their world back, and they've tried over and over and over again. It suggests to me that life causing these mass extinctions, because it did, is inherently anti-Gaian. This whole Gaia idea that life makes the world better for itself. Anybody been on a freeway on a Friday afternoon in Los Angeles believing in the Gaia theory? No. So I really suspect there's an alternative, and that life does actually try to do itself in, not consciously, but just because it does. And here's the weapon, it seems, that it did so over the last 500 million years. There are microbes which, through the metabolism, produce hydrogen sulfide, and they do so in large amounts. Hydrogen sulfide is very fatal to we humans. As small as 200 parts per million will kill you. You only have to go to the Black Sea and a few other places, some lakes, and get down, and you'll find that the water itself turns purple. It turns purple from the presence of numerous microbes which have to have sunlight and have to have hydrogen sulfide. And we can detect their presence today. We can see them, but we can also detect their presence in the past. And the last 3 years have seen an enormous breakthrough in a brand new field. I am almost extinct. I'm a paleontologist who collects fossils. But the new wave of paleontologists, my graduate students, collect biomarkers. They take the sediment itself, they extract the oil from it, and from that they can produce compounds which turn out to be very specific to particular microbial groups. It is because lipids are so tough, they can get preserved in sediment and last the hundreds of millions of years necessary and be extracted and tell us who was there. And we know who was there. At the end of the Permian, at many of these mass extinction boundaries, this is what we find, isoreneritane. It's very specific. It can only occur if the surface of the ocean has no oxygen and is totally saturated with hydrogen sulfide, enough, for instance, to come out of solution. This led Lee Kump and others from Penn State and my group to propose what I call the Kump hypothesis. Many of the mass extinctions were caused by lowering oxygen, by high CO2, and the worst effect of global warming, it turns out, hydrogen sulfide being produced out of the oceans. Well, what's the source of this? In this particular case, the source over and over have been flood basalts. This is a view of the Earth now. If we extract a lot of it, and each of these looks like a hydrogen bomb. Actually, the effects are even worse. This is when deep Earth material comes to the surface, spreads out over the surface of the planet. Well, it's not the lava that kills anything. It's the carbon dioxide that comes out with it. This isn't volvos. This is volcanoes. But carbon dioxide is carbon dioxide. So these are new data Bob Berner and I from Yale have put together, and what we try to do now is track the amount of carbon dioxide in the entire rock record. We can do this from a variety of means, and put on the red lines here when these, what I call greenhouse mass extinctions, took place. And there's two things that are really evident here to me, is that these extinctions take place when CO2 is going up. But the second thing that's not shown on here, the Earth has never had any ice on it when we've had 1,000 parts per million CO2. We are at 380 and climbing. We should be up to 1,000 in 3 centuries at the most, but my friend David Battisti in Seattle says he thinks 100 years. So there goes the ice caps, and there comes 240 feet of sea level rise. I live in a view house now. I'm going to have waterfront. All right, what's the consequence? The oceans probably turned purple. And we think this is the reason the complexity took so long to take place on planet Earth. We had these hydrogen sulfide oceans for a very, very long period. They stopped complex life from existing. We know hydrogen sulfide is erupting presently a few places on the planet. And I throw this slide in, this is me actually, 2 months ago. I throw this slide in because here is my favorite animal, chambered nautilus. It's been on this planet since animals first started, 500 million years. This is a tracking experiment. Any of you scuba divers, you want to get involved, one of the coolest projects ever. This is off the Great Barrier Reef, and as we speak now, these nautilus are tracking out their behaviors to us. But the thing about this is that every once in a while, we divers can run into trouble. So I'm going to do a little thought experiment here. This is a great white shark that ate some of my traps. And we pulled it up it comes. So it's out there with me at night. So I'm swimming along, and it takes off my leg. I'm 80 miles from shore. What's going to happen to me? Well, now I die. 5 years from now, this is what I hope happens to me. I'm taken back to the boat. I'm given a gas mask, 80 parts per million hydrogen sulfide. I'm then thrown in an ice pond. I'm cooled 15 degrees lower, and I can be taken to a critical care hospital. And the reason I can do that is because we mammals have gone through a series of these hydrogen sulfide events that our bodies have adapted. And we can now use this as what I think will be a major medical breakthrough. This is Mark Roth. He was funded by DARPA to try to figure out how to save Americans after battlefield injuries. He bleeds out pigs. He puts in 80 parts per million hydrogen sulfide, the same stuff that survived these past mass extinctions. And he turns a mammal into a reptile. I believe we are seeing in this response the result of mammals and reptiles having undergone a series of exposures to H2S. I got this email from him 2 years ago. He said, I think I got an answer to some of your questions. So he now has taken mice down for as many as 4 hours, sometimes 6 hours. And these are brand new data he sent me on the way over here. On the top now, that is a temperature record of a mouse who has gone through the dotted line, a temperature. So the temperature starts at 25 centigrade, and down it goes, down it goes. 6 hours later, up goes the temperature. Now, the same mouse is given 80 parts per million hydrogen sulfide in this solid graph, and look what happens to its temperature. Its temperature drops. It goes down to 15 degrees centigrade from 35 and comes out of this perfectly fine. Here's a way we can get people to critical care. Here's how we can bring people cold enough to last till we get critical care. Now, you're all thinking, yeah, what about the brain tissue? And so this is one of the great challenges that's going to happen. You're in an accident. You got two choices. You're going to die, or you're going to take the hydrogen sulfide and say 75% of you is saved mentally. What are you going to do? Do we all have to have a little button say, let me die? This is coming towards us, and I think this is going to be a revolution. We're going to save lives, but there's going to be a cost to it. The new view of mass extinctions is, yes, we were hit, and yes, we have to think about the long term because we will get hit again, but there's a far worse danger confronting us. We can easily go back to the hydrogen sulfide world. Give us a few millennia, and we humans should last those few millennia. Will it happen again? If we continue, it'll happen again. How many of us flew here? How many of us have gone through our entire Kyoto quota just for flying this year? How many of you have exceeded it? Yeah, I've certainly exceeded it. We have a huge problem facing us as a species. We have to beat this. I want to be able to go back to this reef. Thank you.
I've got one question for you, Peter. So am I understanding you right, that what you're saying here is that we have in our own bodies a biochemical response to hydrogen sulfide that in your mind proves that there have been past mass extinctions due to climate change?
Yeah, every single cell in us can produce minute quantities of hydrogen sulfide in great crises. This is what Roth has found out. So what we're looking at now, does it leave a signal? Does it leave a signal in bone or in plant? And we go back to the fossil record and we can try to detect how many of these have happened in the past.
It's simultaneously an incredible medical technique, but also a terrifying...
blessing and curse.